In this video, we're going to talk about weather forecasting, and we're going to focus on evaluating 500 millibar maps, and we're also going to take a look at what vorticity is and how to use it in our weather forecasts. So you've heard in other videos of me speaking on this topic before is that 500 millibars to start your forecast, especially when you're starting a forecast from scratch, is a great way to begin looking at your overall bias of the weather for the entire country or the entire region, wherever you're really forecasting for. And I like 500 millibars because it's halfway up in the troposphere, so we still see what the overall jet stream is like, and we can also see all the little short waves that will spawn low pressure systems. So this way we can kind of gauge where our synoptic storms are, or our weather patterns are. And so you can think of it as like looking at your Facebook wall. If you're commuting home and you're really just scanning social media just to see what you've missed throughout the day. You're not necessarily looking for anything in particular. You're really just kind of scanning. And so if you think about 500 millibars being like that, you're really just scanning the atmosphere. You're looking for your bias. You're looking for your troughs and your ridges. And so we've talked about troughs and ridges before, but I would just want to talk a little bit more about 500 millibars. And so on a 500 millibar map, these lines, these isobars, these basically just denote what 500 millibars would be like at different altitudes because of temperature differences. So here you notice 576, 570, 564, so on and so forth. So the closer you get towards the North Pole, the cooler it is, and therefore the lower 500 millibar heights you have, meaning that the lower 500 millibars would be in the atmosphere because the tropopause is compressed more. And then when you look at the south here, you notice that you have higher or thicker 500 millibar heights. And so that is because the troposphere is actually warmer, so the atmosphere or higher, and that's because the atmosphere is actually thicker. So when we look at this, that's where we can denote where our ridges are and where our troughs are. But there's a lot more that can be evaluated just from 500 millibar maps. And so when we talk about temperature or forecasting temperature, you always want to look at either MOS, or you want to use the National Weather Service grids, or you want to look at a weather model, but you want to zoom in at the surface. But for 500 millibars, depending on what time of year it is, you can actually figure out what the temperature would generally be. And so what you notice here is that in the southern plains of the United States here, you notice that it is under this 576 millibar contour, a height contour. So what you can gauge from this is we're experiencing warmer than normal weather, we're experiencing dry weather. And a great rule of thumb is that if you forget the zero, and you won't always see zeros at the end of these 500 millibar heights, but if you ignore the zero and you take the last two digits out of the number, so if you take 576 and you take the last two digits, you can use that as a bias for what temperature trend you may or may not be looking for. So here when we talk about 576, and we look at, like, say, New Mexico, Colorado, Arizona, the four corners of the United States, for November, we're expecting 70s to be the main temperature range in this area. Now you go up to the Northeast, here we see 528 millibars. So we know that it's generally cooler, and here we also have a trough, and here you can almost see a little closed off circulation, so this would be an upper level low. But back in the Northeast, it is significantly cooler and may not necessarily be in the 20s. So here we have 528, between 522 and 528. So it probably isn't necessarily in the 20s for mid-November, but it's probably in the 30s, which is considerably cold and much cooler, or much below normal for the Northeast for the month of November. So when we talk about vorticity, vorticity is really just a rotation in a fluid. So these are the short waves within the long waves, or the little rapids within the jet stream. And so what vorticity is that there are the parents of low pressure systems. So this would be a 500 millibar vorticity map of the United States, and this is for May 29th. And so what you noticed here is that here you have a large ridge over most of the United States, or a good chunk of the United States. So most of the United States is experiencing above normal temperatures. And so this is Memorial Day weekend. And so you can see how most of the United States is really enjoying Memorial Day weekend. But here on this map, you can see where the X's are. You can see that this is the center of the shortwave. And you notice that they're always located in the troughs. All these X's are located in the troughs, or what would be a trough. So here, when we look at this, remember, if we cut this trough in half, low pressure is on the right-hand side and high pressure is on the left-hand side. Same thing here. Here's a little trough, cut it in half. Low pressure is on the right, high pressure on the left. See the little ridge, little trough, little ridge, and then here's what we call an inverted trough, which is a trough on its side. Cut the trough axis in half right here. We have two little vortices right there, and then we have a much bigger one up in the Canadian Maritimes. And then we also have a little cutoff low down in Louisiana and Arkansas, down and through here. So those are points of vorticity, and so vorticity is very useful because we can use vorticity and upper level maps to really form a very nice bias. So when we look at a vorticity map, and there's multiple ways to look at vorticity maps, at 500 millibars, what you see here on this example is here's the jet stream. Sorry for moving that. Here's the jet stream, like so, and notice the highlighted area, or the circled area in black. Here would be a strong area of vorticity, so we expect a relatively strong area of low pressure just towards the right of that. And here, when you look at the surface, this is exactly what you see. And so here, also marked off in black, you see that here is a quite strong area of low pressure up towards the Great Lakes. So it's important to note that when you look at a 500 millibar map, you can gauge who is warmer, who is colder, where my high pressure systems should be, and where my low pressure systems should be. So out here over California, this would be a ridge, so we should experience high pressure, and you see nothing but high pressure along the entire west coast. Same thing for the east coast. Here, nice giant ridge over the east coast, and that's what you see here, a nice giant ridge, or almost a maritime high out in the Canadian Maritimes. So nice and dry, relatively cool, but nice and dry for the east coast. Okay, and so this is how you evaluate upper level maps using vorticity. And if you know where the vort max is, or the center of the shortwave is, then you know where the low pressure system is. So just to sum things up, here when we have a zonal jet stream, or a very flat jet stream here, you see that there's really no waviness to it. And yes, we have differences between cold and warm, and we have a little bit of a trough here, but this is almost flat. When you have more curvature here in the jet stream, or where the trough axis should be, remember, I have my low pressure on the right-hand side, I have my high pressure on the left-hand side. Air is converging at the surface, it's converging aloft here, and then diverging at the surface, and then on the right-hand side, my wind is diverging aloft because it's converging at the surface. So when you put a low pressure system, or when you draw a mid-latitude cyclone on this, you see here that here would be where my warm front is, and it makes sense because my air is rising and diverging aloft. Here my air is converging aloft and diverging at the surface, creating high pressure, and this is where my cold front would be, because cooler air is more dense. And so that would be the entire picture. When you look at upper levels and you relate it to a surface map, that is the correlation. So when you look at airflow, here would be my jet stream. So here, wind comes down, wind is converging. If it's converging at the surface, it's diverging aloft. So wind is diverging aloft here to the right of the trough axis. All the wind is clear to go, accelerates again, and therefore wind is diverging aloft, which is converging at the surface, rising up. So this is where my area of low pressure would be. So when you put the upper level maps together and you overlay them with the surface maps, you can really get a good understanding of what's going on. But the upper level maps are actually essential, and it's really the first point or the first piece of information you look at when you create a forecast, because you can gauge so much of what's going on in the atmosphere by just looking at one 500 millibar map. Then when you get into the more finer details, then you can use things like MOS to predict your temperature and wind and cloud cover, and you can look at more surface parameters on a weather map using any of the weather models. But 500 millibars is really where you should start your forecast.